my channel. This is the 12th episode of the Meet the Pro series, a series where I interview professionals in the field of biology and genetics to help high school students interested in the field. In today's episode, I will be interviewing Dr. Daniel Dittoro. He is a postdoc in the Pillay Lab at the Reagan Institute of Harvard, MIT, and Mass General, a clinician at Mass General, and a life sciences consultant. And I'm delighted to have him with me here today. Thank you for being here, Daniel.
Thank you very much for inviting me.
Okay, so in college, when you first started, you were a swimmer, correct?
Yep.
Okay, so how does that transition come about? Like you go from D1 swimmer to scientist. Like how does that work?
It was bumpy with a lot of false starts, multiple failures, and it took a long time. It was not an easy transition. I I studied molecular biology in undergrad, but I chose my major for a very immature reason.
Okay.
I chose it because I wanted to distinguish myself from the pre-med students who I felt only cared about grades and weren't really interested in learning the
Yeah.
material.
Yeah.
And molecular biology was the hardest biology major we had at my
Mm-hmm.
school. You had to take engineering, biochemistry. You had to take, multiple calculus courses. You had to take engineering, physics. We had to take PChem. And so I picked it for a really stupid and immature reason, but I got lucky because I really, really liked it. So I really enjoyed
Yeah.
it. But I didn't have a lot of time for research because of my training schedule. So I didn't get to do much.
Mm-hmm.
The main thing you do with a molecular biology degree is go to grad school. But I had spent like barely any time in lab, and mostly I was just doing like PCR cloning, really boring stuff. So I knew I needed some more experience before going to grad school. I did this 6-month internship at the European Molecular Biology Labs in Heidelberg in Germany,
Yeah.
but was really bored with it. I had a great trip. I enjoyed my time there, but I was not in love with molecular biology at that point. I thought I would be. I wasn't. I was
Mm-hmm.
worried. What am I going to do? So I ended up, instead of going to grad school, I taught high school biology for a year. And in that process, I loved working with kids, and I thought, I know what, I'll be a pediatrician. I can sort of marry the science and working with kids. I get to do both at once. Pediatrician, that's right for me. But since I wasn't pre-med, I had a bunch of work I needed to do before I could apply to med school.
Yeah.
So I decided to get a job in a molecular biology lab, which I could get because of my degree and my experience, and use that to work towards going to med school. I could take
Mm-hmm.
classes, I could take my MCAT, have something on my CV that helps get into med school. And that, again, I got really lucky. I got a job in this guy Shane Crotty's lab. He is an absolutely fantastic scientist. And all of a sudden I found myself where I thought I would be coming out of undergrad in this amazing lab, doing amazing work, falling in love with science again.
Yeah.
But then it took me 3 years to get into med school. I applied 3 years in a row. I didn't get a single interview the first 2 years.
Okay.
But it took a lot of time. It took a lot of time and a lot of work. And it wasn't easy. Multiple years of failure and struggle and frustration, but the investment was worth it because it ended up working out great.
What was that like the X factor that helped change the result going from year 2 to year 3 that eventually got you into?
So big difference was, instead of applying straight MD, I applied to MD PhD programs,
Okay.
which superficially is more competitive,
Mm-hmm.
but was actually much better suited to my own personal track record and my experiences. And then
Okay.
also having that time as a lab tech to really think about what I'm doing, why I'm doing it, what I want to do in the future. By the time I was writing that essay the third year, I was actually speaking with confidence,
Yeah.
yeah, I really knew what I wanted to do. I knew how to do it, and I was going to go do it.
Hmm.
And it didn't matter
Okay.
what anyone else said.
Yeah.
And
Yeah. Yeah.
you read a lot of these application essays, like it's really easy to tell when someone knows what they're talking about.
Yeah. Okay. So I forget if you mentioned this in the previous question, but you were in Shane's lab. You were a research tech. Was that
Yep.
what it was?
Yep.
And then you went research tech to MD PhD.
Yep.
Okay. Now I know that as like on the side, you also do like consulting. So could you talk a little bit about that?
Yeah, absolutely. As so many other good, fortunate events in my life, this one was serendipitous, like getting hired by Shane, complete
Yep.
accident. Um, Falling into the orbit of these guys also was total serendipity.
Mhm.
But met some guys that run a business investing in the biotech space. Talked about one thing that led to conversations about another. Now we're having dinner, and they're feeling me out, and they ended up hiring me to do some consulting work for them. And the basic premise of the position is that the market value of biotech IP is very strongly influenced by phase 2 clinical trial results, understandably so.
Yeah.
And um, there is tremendous value in being able to anticipate clinical trial results,
Mhm.
essentially to identify opportunities to invest either before prices go up or alternatively after prices have gone down, right? If a compound fails in a clinical trial, the market for it essentially bottoms out, right?
Okay.
But if that compound or that piece of intellectual property has value in other applications
Mhm.
that might not be priced in, right? So you have like a failure in one application, the price tanks, but there
Yep.
might be value in other applications, and so you might be able to get a piece of intellectual property far below its true market value.
So you just like it's like capitalizing on that moment when.
Yep.
Okay.
Yeah. So I try to figure out: do I think it's going to work? Do I think it's
Mhm.
not going to work? If it
Yeah.
is going to work, will it work in other things? If it's not, will it work in other things? Yeah.
Okay.
Yeah.
So now you're at the Reagan.
Yeah.
How did you first meet Shiv?
Uh, on Zoom,
On
as is
Zoom.
so
Okay.
often the case these days.
Yeah.
Shiv, I was looking for a lab to do my work in. I had very specific things that I wanted to do. I was shopping around at the various labs in the Boston ecosystem.
Mhm.
And Shiv put out a very nice paper on a related subject. And I shot him an email and said, "Hey, saw your paper. Have some ideas, looking for a lab, want to talk." And I got about sort of 5 minutes into my pitch when I was meeting with him, and he just said, "Daniel, that's enough. I've heard enough. Like, this is great. It sounds awesome. You come to my
Okay.
lab, do whatever you want to do."
Can you talk about say two of your projects, your two most favorite projects that you're working on right now?
Yeah, sure. I got a couple cool ones. All right. So when a T cell gets activated, it has to make two choices. One, it's going to drive inflammation. Two, it's going to suppress it. And then separately, it's going to drive humoral antibody responses,
Mhm.
modulate humoral responses, or cellular responses. These bifurcations are sufficiently independent such that you get four outcomes: pro-inflammatory humoral, pro-inflammatory cellular, anti-inflammatory humoral, anti-inflammatory cellular. I got one project that's looking at the um, suppressive versus pro-inflammatory bifurcation, and another that's looking at the humoral versus cellular bifurcation.
Mhm.
So we'll start with the suppressive one first. So basically, uh, in the 20th century, there was a massive transformation of medicine with the advent of two different things: antibiotics and vaccines. These two things changed the world. And vaccines, all of the approved vaccines to date, all function by driving inflammation to specific targets. The capacity to suppress inflammation to specific targets would also transform medicine. Think about things like food allergies, peanut allergies, autoimmune diseases. There's a million different possible applications. And I think that the 21st century will be the century of tolerogenic vaccines, much as
Okay.
the 20th century was the
Yeah.
century of pro-inflammatory vaccines. And so one of the things I'm working to do is to generate a modular and customizable tolerogenic vaccine
Hmm.
platform. And we think we've found a way to do this. We're not the only ones. There are other groups doing
Yeah.
this as well. And I have decided, because of the history of Brigham and Women's in the transplant medicine field. So the first ever successful solid
Hmm.
organ transplant took place at Brigham and Women's. We have a very well developed transplant immunology department here.
Yeah.
Because of that, because of where I am and who I know, it makes a lot of sense for me to go into the transplant space. So essentially, I'm trying to make a vaccine to prevent transplant rejection.
Okay.
And I think it's going to work.
Yeah.
We
Yeah.
have
Yeah.
preliminary data. You helped me do this.
Hmm.
It looks absolutely fantastic.
Yeah.
So I think we can selectively turn off immune responses to the mismatch epitopes in the transplanted organ.
Hmm.
If so, you could then free all of these patients from lifelong immunosuppression. And we might also be able to relax the stringency of the matching requirements and sort of, loosen up the backlog of cases and get organs into recipients quicker. So that's one project, a transplant rejection vaccine.
Yeah.
And then the other
That's
um,
the tolerogenic is the transplant rejection.
Yep. Yeah.
Okay.
Tolerogenic just
Yeah.
means it's creating an environment of tolerance. Tolerance is maintained by the suppression of
Of the
inflammation. So
immune. Okay.
a
Gotcha.
suppressive
Yeah.
vaccine is a tolerogenic vaccine.
Yeah.
And then the other project, I'm looking at this whole humoral antibody versus cellular reactions. And in pro-inflammatory cells, that's TFH versus non-TFH.
Hmm.
I want to understand what drives this TFH non-TFH bifurcation. I
So
have a
what
whole
is a for our
yeah
audience members? What is a TFH, and then what is a T cell? Sure.
Yeah. So a T cell is an immune cell that develops in the thymus,
Hmm.
thymus T cell. And when they come out of the thymus, they come out as these naive T cells. Naive
Yeah.
T cells are supposed to be sort of they're pluripotent cells, and they kind of float around the body, checking out the organs, going in the blood, going in the lymph nodes,
Yeah.
and essentially just waiting. And if the right antigen gets presented to them, they can get
Hmm.
activated. When they
Okay.
get activated, they can drive an immune response. And there's really two major kinds of pro-inflammatory T cells. These TFH. TFH means T follicular helper. What's
Okay.
a follicular helper? Well, it's a one that helps a follicle. The follicle is the B cell area in the
Okay.
lymph nodes. So
Yeah.
essentially, TFH help B cells,
Hmm.
and then non-TFH, they go to the site of inflammation
Yeah.
and they help all the other stuff, the neutrophils, the
Okay.
macrophages, the epithelial cells, stuff like that. Okay.
Hmm.
So one kind of hangs back and does B
Yeah.
cells. The other goes to the site of inflammation and manages things there. Um, and every single vaccine that's ever made it to market depends on the ability to drive TFH, right? All these vaccines that we know about and that we take all require antibody production, and that antibody production is dependent on the T cells, specifically the TFH. So
Okay.
understanding this TFH non-TFH bifurcation is really, really important for vaccine design. And I want to
Okay.
understand it better. And so I have a bunch of preliminary data that we're hoping to submit for publication soon that shows that this TFH versus non-TFH bifurcation is actually the very first thing that happens when a T cell gets activated, which is kind of crazy. There's sort of decades of literature that would argue against that, but nevertheless, that seems to be the case. And in fact, it was happening
So
so early. Yeah.
sorry, just to clarify. So when you said the bifurcation is almost immediate, you're saying
Yes.
that when you have a naive T cell, it's coming out of the thymus.
Yep.
One of the first things it does is decide if it's going to be TFH or non-TFH.
Yep.
Okay.
Once it gets activated, when it gets
Yeah. Yeah. Yeah.
activated, the
Yeah. Okay.
first thing that happens is
Okay.
this TFH versus non-TFH thing. Before anything else is going on,
Hmm.
that's already starting,
Yeah.
and it all is it's basically the result of the strength of activation. the strength of activation will lead to differential expression of gene expression filters that feed back on each other, and you end up with like
Hmm.
a binary outcome from a normally distributed continuous variable.
Yeah.
Uh, so that's really amazing that it's like literally the first thing that's happening, and in fact, it was happening so early that it made me curious that maybe there was actually pre-existing heterogeneity in the naive cells that biased this outcome. And so we did a bunch of single cell RNA sequencing on
Hmm.
naive T cells. Now, canonically, naive T cells are all the same thing, right? They're
Yeah.
treated as a homogeneous population. A
Hmm.
naive T cell is a naive T cell is a naive T cell. But it turns out that's not true. There's actually a whole bunch of different kinds of naive T cells.
Okay. Okay.
And what kind of naive T cell you are really strongly biases what you do when you get activated. So,
So
like,
this part, this naive T cell heterogeneity, like the difference between them, that is already existing even before they get activated.
yeah, exactly,
Okay. Okay.
exactly.
All
Which is
right.
super wild.
Yeah.
Uh, so we've already got all this heterogeneity, and it really dramatically biases what they do. Like if you're this kind of naive T cell, you have this percent. You got like an 80% probability of making IL-2 and becoming a TFH. If you're this kind of naive T cell, you've got like a 20% chance of making IL-2 and becoming TFH. So it's
Okay.
a really big bias.
Mm-hmm.
And okay, well, that begs a pretty obvious question, like where is that coming from? When
Yeah.
did that show up? All right, so we go TFH and non-TFH all the way back to like right at activation, and then we
Mm-hmm.
go, oh wait, no, actually, in fact, there's already bias there before activation. Well, where is that bias
Yeah.
from? And we conceptually organized possible sources into two categories. One, central processes. When I say by central processes, we mean in the thymus during thymic development,
Okay.
or peripheral processes, by which we mean after egress from the thymus. All right.
So
So to
both of
ask,
these, sorry, the central and the peripheral, those are two things that are going to create diversity within naive T cells.
yeah, I mean, there's a lot of potential sources and mechanisms. So you want to try to like organize your thoughts so that you
Yeah.
can ask questions in very sort of systematic ways. So we can just say,
Mm-hmm.
regardless of what all the possible sources are, we can say that they're all of two kinds. One is central process and one is a peripheral process. So
Mm-hmm.
we can ask about the central processes really easily, right? We can go into the thymus and we can look at the cell stage right before it leaves the thymus. So, like literally the very last stage of maturation, right before it leaves, and just ask, is the heterogeneity there already? And sure enough,
Okay.
it is. So, we
Mm-hmm.
already see the heterogeneity that we see in the naive T cells in the periphery is already there in the thymus. So, that really strongly suggests that there's a thymic source, right? Um, and
Okay.
so we got a bunch of data now that suggests that so in the periphery with the naive T cells, right, it's the strength of stimulation that does this TFH non-TFH.
Mm-hmm.
And what we see in the thymus, it's the strength of stimulation during positive selection
Yeah.
that is imparting this heterogeneity. So it comes back to the exact same
Mm-hmm.
mechanism as before. It's the strength of stimulation. So strength of stimulation in the thymus during selection imparts some of this heterogeneity that persists into the periphery, and then strength of stimulation of a
Yeah.
naive T cell in the periphery reinforces the whole thing and just keeps it going
Yeah.
forward.
Okay. Damn.
Yeah, and then right, that's the presence of a central source, but that's
Mm-hmm.
not mutually exclusive with a peripheral source. So then we want to
Yeah.
ask, is there a peripheral source of this
Mm-hmm.
heterogeneity as well?
Mm-hmm.
And one of the main markers that we see on these naive T cells, differentially expressed markers, is the IL-7 receptor. And that's super convenient for us because IL-7 is like the main cytokine that's required for naive T cell homeostasis. They need this thing to stay alive. They see it every so often. So they get a naive T cell, it gets a little tickle of self antigen, it gets some IL-7, that keeps it alive for a couple weeks. It surveys everything. And
Mm-hmm.
after a couple weeks, it needs to get another little tickle of antigen, another little bit of IL-7 to keep it going. And so what we found is that um, uh, treatment with IL-7 will shift the naive heterogeneity. So we think part of the heterogeneity is how strongly it gets stimulated in the thymus, and then
Yeah.
part of it is how recently they've seen IL-7 and self-antigen.
Okay.
Yeah.
Um, I want to backtrack a little bit to
Yeah.
the transplant project. Something you
Yeah.
mentioned was that if this works, after you do like more repetitions of that experiment, if it works, then we can help make more like actual drugs in the industry for people to get to help mitigate this rejection. Why do you think that right now, like, there are so few immunotherapies that are actually reliable in the market? Like over
Yeah.
the summer, I remember talking about how, like, even if you take transplant rejection, you were saying how a lot of the drugs are very global.
Yeah.
Um, it's 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 weakening the immune system on a global level, just getting rid of it almost completely, and so that we can tolerate the organ, but in exchange, we lose all all immune strength, and we're basically very susceptible to any
Yep.
disease or infection.
Yep.
So
Yeah.
why
I
do you
mean,
think?
sledgehammers are valuable because sledgehammers work, right?
Yeah,
A big enough hammer, you can break anything.
yeah,
Problem is, everything's broken afterwards. So a lot of the drugs on the market today are just sledgehammers,
mm-hmm.
and it just so happens that you know taking these sledgehammers sucks, but for a lot of people, the consequences of the sledgehammer are a lot better than the consequences of the disease that they had before, right?
Yeah, yeah, yeah.
So it's better, so we do it. But even like these early biologics that we see on the market now, they're still just like slightly more pointy hammers, right? They're not really targeting a specific subset of cells. They might be targeting a cell type or a subset of cell types, but
Mm-hmm.
they're not targeting just the cells that we care about. So they still have pretty big side effect profiles, and they might also have sort of limited efficacy. Like, steroids work really well because they suppress everything.
Mm-hmm.
Problem is they suppress everything. Then you
Yeah.
get like a drug that targets one type of cell. Well, targeting one type of cell might not be enough for the whole effect. Um,
Okay.
so you might have some more limited efficacy, and you still have a side effect profile. What we really want is to be able to target all of the cells that are involved in the reaction, but nothing else. T
Okay.
cells are a great way to go about that because
Yeah.
T cells essentially work as sort of like the field marshals on the battlefield. They're the ones telling everyone else what to
Mm-hmm.
do. So if
Yeah.
you can reprogram the T cells, then everything else will change too.
Yeah.
And T cells are all antigen specific, and that's where these vaccines come in. So
Mm-hmm.
if you can make the reprogramming of the immune system specific to the antigens you care about and the T cells you care about, all
Mm-hmm.
the other cell types will be affected downstream. Um,
Okay.
yeah. So yeah, we have extremely crude drugs. Then some of these biologics, they're still incredibly unsophisticated, right?
Mm-hmm.
It might sound fancy. Oh, it's a new biologic drug and it's really expensive and it's like the next, coolest thing. But still, in the grand scheme of things, they're extremely
Yeah.
unsophisticated tools, and we have to get much better. Antigen-specific vaccines are one way to do that. It's not the only way, but
Yeah.
it's one way to do it.
Okay.
Other
So
people are using like cell therapies. That's another really cool way to get specific. I don't know if you know anything about like cell
no,
therapies and autoimmune disease. Do you know what cellular therapies are?
no.
Okay, so like you ever heard of CAR T cells?
I heard about them, but also don't know what
Yeah.
they are.
Chimeric antigen receptor T cell. That's where you take T cells, just like
Mm-hmm.
regular old T cells, just
Yeah.
all of them, and then you stick in a receptor for the thing that you care about. So you're like retargeting them.
Oh.
Okay.
Okay. All
Yep. So
right.
you can target them to the thing that you want. So it first came around in cancer. So you can
Mm-hmm.
make T cells reactive towards the cancer.
Like the tumor
And,
antigen.
they'll go kill everything. They kill
Yeah.
all of it. It worked really, really well. It kills the non-cancer B cells too, right? It was first
Yeah.
done with B cells. So you program the T cells to target B cells. They kill all the B cells, the cancer ones, the regular ones. But that's great because the cancer would kill you if you don't kill it. So
Yeah.
that's a positive. And more recently, people have been using the same conceptual approach in autoimmunity. So if you have an autoimmune disease that's
Mhm.
driven by B cells, well,
Okay.
let's stick in the same CAR T cell that we use for the B cell cancer, but we use it for the B cell autoimmunity, and it works
Mhm.
really, really well. So that,
How does that? Because um, in the very little understanding I have of autoimmunity,
yeah,
if you have the immune system is attacking us,
yep.
so how do you get the immune system that's attacking us to attack itself? Because you're getting
That's what the chimeric antigen receptor does, that CAR cassette.
yeah.
So you're going to take the patient's T cells, you're going to put in a receptor to the B cells, and you're
Mm-hmm.
basically reprogramming the T cells to go
Okay.
kill B cells instead of whatever they were killing.
Yeah.
When they kill off the B cells, that can really help the disease,
Mm-hmm.
right? Have you heard of rituximab?
No.
So it's an anti B cell antibody that you can use to deplete B cells.
Okay.
So that's like one approach, right? You've got chimeric antigen receptors, then you've got depleting antibodies, and you can have vaccines.
Mm-hmm.
The depleting antibodies, though, sometimes they work really well, but other times they don't, and it might have to do with like depth of depletion. These chimeric antigen receptor cells probably get a better depth of depletion. So there's been a bunch of like really high visibility papers lately where people are using CAR T cells in autoimmunity, and it's kind of cool because like you think autoimmune diseases aren't just a result of B cells, and all these are doing is killing B cells. So if we're only killing like one of the cell types involved in the response, why do we
Yeah.
get such a profound effect? But it turns out, right, the B cells do more than just make antibody. The B
Mm-hmm.
cells actually are really important for presenting antibody to the T cells.
Yeah.
So it's kind of crazy. You make the T cells kill the B cells, which because then they're not presenting antigen to the T cells, kills the
Oh.
T cells too.
Yeah.
And when you kill the T cells, you affect all the cells in the response.
And then you don't have any autoimmunity after that.
Oh, you froze. Oh no, I lost you. Oh, there you are. You're back.
Okay. Well, yeah. All right. I have
Oh,
one last question. Do you
yeah,
hear me? Okay. I have
yeah.
one last question. It's like a more of a fun question, I guess.
Okay.
But if you could choose any extinct species to bring back, which one would it be and why? And you
Oh,
cannot say
man.
dinosaurs
One species.
or animal. It doesn't really matter.
Wow, that's a really good question. I don't know. I'm gonna have to think about that because there could be like really profound implications for bringing back something interesting.
Yeah.
Oh man, I don't know. Can I think about that on the train home and tell you because I
Sure.
can't pick just one right
Sure.
now.
Why not? Yeah. I once I remember like there was it was either a paper or a talk that I saw. But basically the dude was trying to bring back woolly mammoths.
Yeah, yeah.
Um, I thought that was pretty cool. So yeah.
There's a guy. He has a great TED talk. He's out of like the University of Wisconsin or North Dakota. I don't remember. Middle northern part of the country, but he's trying to do the whole Jurassic Park thing by bringing back dinosaurs. But he's got a
Okay.
kind of a cool approach to it. So instead of like trying to get dinosaur sequences and then make germ cells with them, he's
Hmm.
going backwards from the chicken said, okay,
Oh,
chickens are
yeah,
avian dinosaurs. They're
yeah,
evolved from dinosaurs. So if we can infer the earlier sequences, we can reincarnate dinosaurs that way. So
yeah.
yeah, there's a dude actually trying to make dinosaurs from chickens,
Okay.
which is a pretty awesome project.
Um, all right. Yeah. Might have a T Rex walking around sometime.
Yeah,
Okay. I don't want to use up too much of your time.
yeah.
Thank you. I really appreciate this.
Thank you.
Yeah, I had a great time.
Yeah, great. I'm glad it was fun having you.
Yeah.
All right, see you later, dude.